Yeah, so thanks again. It's your fault. You voted to hear more about DarkSUSY rather than about the dark matter problems. So I thought I'd do this in two parts, like a short part, which is more of an introductory, you can say commercial, about what DarkSUSY can do, just give you some examples. So this should also be online now, if you want to follow. So just to give you sort of some idea of what DarkSUSY is, to start with. Okay. So what we want to do, in the context of dark matter, is basically, compute rates. Yeah. So I talked about production mechanisms of dark matter, but what you really want to have is a concrete model. You want to calculate the production. You want to make sure that you choose your parameters such that you can explain the observed dark matter abundance, and then, given those parameters, you want to compute various rates, direct detection, indirect detection, maybe production rates at colliders, or also astrophysical probes. I mentioned them all along, for example, from the cutoff scale in the matter power spectrum, or dark matter self interactions, these kind of things. So the typical, I definitely can't do everything here. The typical workflow is that you start with your particle physics parameters. You define a model. It can be a different model defined by some number of parameters. Then from the Lagrangian input parameters, you want to calculate the actual masses and couplings that are relevant in the model. That can be arbitrarily complicated or simple, depending on the degree of sophistication you want to use. And then you want to calculate the correct dark matter abundance and rates, as you said. And in the end, of course, you want to compare to data. So which part does DarkSUSY here? Well, almost all of this. Very little focus on accelerator constraints. This is basically linking to external tools. Strong focus on these parts, and definitely not this part. So it's about a rate calculation, which you then can link to tools that do global parameter scans like Gambit, for example. So that's basically the general framework. Okay, so technically, what is it? It's a Fortran library, yes, Fortran. And it's not as bad as it sounds. There are good reasons for keeping Fortran, apart from the fact that this is what it has been and no one wants to rewrite it, unless any of you volunteers. So we tried to make it actually very modular, which also sounds like very non-Fortran, but I would argue that it has become a very modular code, and that's what you can try today. One of the most, important reasons for using Fortran is, of course, that it's fast. So whenever we have complicated integrals or multiple integrals of the types that I've been talking about, it's actually a good idea to use Fortran, just because the numerical routines are faster. And there are many examples of things that this code can do, which simply wouldn't work in the lifetime of your PhD if you implemented it in other languages. Okay, so then actually you can also wonder about the name, DarkSUSY. That's historical. It comes from the times. That's when the code was conceived, when everyone was sure what dark matter is, namely a WIMP, more specifically the lightest supersymmetric particle, the neutralino. And that's where this name comes from. So since version 6 of the code, which is a couple of years old now already, it has been completely de-SUSYfied, meaning that there's a split between sort of the main part of the library, which is independent of the given particle physics module, and specific particle physics modules. Of course, we still have the MSSM implemented, so we can do all the SUSY stuff that we could do before, but then there are also other models, and most importantly, it's relatively straightforward to just add your new models in an effective way. Okay, so just to give you some ideas of what we can do, so this is relative density calculations. That's what we've been talking about in the lectures. So by relative density routines here, I mostly refer to freeze-out kind of scenarios. There are freeze-in routines. DarkSUSY has fully included routines for kinetic coupling, decoupling, and the corresponding calculation of the cutoff in the matter power spectrum. So you just specify your model, you get all these things out, omega, dark matter, cutoff, scale, and so on. And just to add here, like the more non-standard things that you cannot that easily find in other codes is, for example, support for arbitrary dark sectors, which can have different temperatures, not just with a fixed temperature ratio, but an arbitrary temperature evolution in the dark sector. Coupled Boltzmann equations are implemented, so the kind of exceptions that I mentioned at the beginning of this lecture. Asymmetric dark matter is a recent addition, and so on. But then there's much more. Direct detection routines, new feature added. There has been some activity related to what is known as cosmic ray accelerated dark matter, which gives you the opportunity to test sub-GeV dark matter particles because of interactions with cosmic rays. I think this is the only public code that can do this, actually. I will give some examples of this. Propagations routine for cosmic rays, self-interactions, capture rates, indirect detection rates, and so on. So this is just some list, and I will later give some examples. So when you download DarkSUSY, most of you have done this, all of you. You can see the current version. Every new version comes with one more or less significant new aspect. So make sure that you always use the most recent edition because it's actually a quite active development going on. Okay, so then the first thing that you would typically do when you start to get in touch with the code is what I've suggested already also in the exercises, to look at the example programs. So this is the best way of getting to learn the code. There are like two main programs where the idea is to have sort of a detailed or a summary of typical calculations that you can do. You can run them. This is also what is done when you perform the test after the installation, basically calculating all kinds of rates and compare it to saved reference values to just check that the installation went right. And the nice thing is here that, we will get back to this, but you can use the same program to calculate all these observables for different particle modules. But then, from a pedagogical point of view, often much more relevant are these sort of more minimal applications that do very specific things, like calculating direct detection rates, calculating the flux in the neutrino spectrum that you get from the center of the sun, calculating, for example, the relic density. You can check the difference of standard freeze out with coupled Boltzmann equations and so on. So these are all examples that are rather well documented. So they are meant to be documented in a pedagogic way and to help you to get an idea of what is going on and how to use the code. So the typical way you would start using the code is by looking at one of these examples, run them, understand very, very roughly what is going on, and then just to modify things like line by line even to see what you can do. And then you get an expert after a while. Okay, so I just want to give you a few examples to connect to what we've talked about. Relic density, we've seen the Boltzmann equation. As I stressed, this is only valid in kinetic equilibrium, but we also have routines beyond that. And I mentioned in passing that this form of the freeze-out equation, the Boltzmann equation, is actually valid also in much more complicated situations when you have co-annihilations, so an entire network of particles that decay then to the lightest one. So numerically, you can formulate everything in terms of one free function, which is referred to as an effective invariant rate. And that is a typical example of what I will later refer to as an interface function. So the entire model-independent part of the code, so doing thermal averages, solving the Boltzmann equation, and so on, doesn't have to know anything about the particle model. It only has to be provided with some numerical function. This numerical function can be computed in a given model, like the MSSM. It can be very, very complicated. But you could also, for example, provide it in a numerically tabulated form. If you take it as input from somewhere else. You could still use all the routines, the model-independent routines from DarkSUSY. So that's the general strategy. We have freeze-in production, and as I stressed today, the main conceptual change is then that this invariant rate doesn't only depend on the momentum or center of mass energy, but additionally on the temperature. that you can reformulate in terms of a Lorentz boost dependence. Okay, to just give you some example plots produced with DarkSUSY, I mentioned that it's actually important to take into account these quantum effects. So this is the freeze-in coupling and the scalar singlet model that you need in order to get the right relic density. And here you see the difference depending on whether or not you take into account these quantum mechanical quantum statistics effects. So it's at the level of like 10–20%. So it's sizable with respect to the observational accuracy. It's also an interesting model because you have to take into account additional temperature effects. There's actually a phase transition. The standard model, electroweak phase transition. At high temperatures, this model is just a 4-point interaction. We have the unbroken phase where you just have a 4-point coupling of the dark matter particles to the standard model Higgs. But then after symmetry breaking, we have the actual Higgs boson that we've seen. And the coupling is mostly, or the process is mostly through this S-channel resonance here. And the freeze-in routines take all that into account with a temperature dependence that takes into account how the phase transition happens. So it's at this level of detail that things are implemented. This is a plot that shows here one of the later comments that I made about freeze-in, that if you have a very late reheating, in this kind of situation, so late reheating means after symmetry breaking has taken place, and if you then think of like GeV or even sub-GeV temperatures, then of course the Higgs mass is very heavy, so this becomes an effective dimension 5 operator. So we are in the situation where we actually have a higher dimensional operator, so UV sensitive freeze-in. And that is why in these cases we are sensitive to the reheating temperature and would reproduce even with freeze-in the correct relic density only with relatively large couplings, which are testable by other means. Self-interactions. Just an example here is a dark sector model that you could test. So you have, as a toy model, you have some coupling of the dark matter particles to some new gauge boson, some U1 prime, and then you can, for example, say that you have an additional coupling of this U1 prime to the heat bath. This could be active neutrinos, but these could also be sterile neutrinos, so really a complete dark sector model. So what's happening then is that you have these kind of annihilations at tree level directly into the vector bosons. That's one of the examples I was sketching, but then you have to take into account the Sommerfeld effect due to multiple exchanges of these vector bosons, and in principle at late times these vector bosons could decay then into, for example, sterile neutrinos or active neutrinos, potentially giving you indirect detection signals. The exchange of the vector boson also triggers self-interactions, which we can handle and which you can compare to observations. And since you have a coupling to, not to the battery of my presenter, so the rightmost plot that is elastic scattering with the heat bath particles, and if you have a light mediator with sizable couplings, that means that you have very late kinetic decoupling. So that kind of model was interesting in the context of the so-called small-scale problems in cosmology, which are sort of fading away, because it's the first example of a model that could actually, of a very simple model, that could actually address all these small-scale problems simultaneously. So how does that work? Well, basically, it's a simple model where you have only 3 parameters, the dark matter mass, the mediator mass, and the coupling. And then if you fix the relic density, that's only 2 parameters left. And you need to take into account all these effects. The Sommerfeld, in fact, you need to take into account that the dark sector temperature actually varies. It's not the same as the standard model temperature. And the way it varies depends on how the number of degrees of freedom changes in the dark sector and the visible sector. And all of this is handled automatically in the code. So then you can plot everything. The coupling is, do we have another presenter here? Or just batteries? So the coupling is fixed by the relic density, and then the parameter plane is just the mediator mass versus the dark matter mass. And then we can, everywhere in this parameter plane, we get the right relic density. And then we can compute the late kinetic decoupling that we have in this case, from that the cutoff mass, indicated here in terms of solar masses. So this is a 10 to the minus 11 and 10 to the minus 10 solar masses. Yeah, so if the cutoff is too small, so you exclude everything so the labeling is wrong here. Yeah, so this is 10 to the minus 10 and this to the minus 10 to the minus 11. Yeah, so if the cutoff is too large, yeah, you would even exclude structures at the level of dwarf galaxies. Yeah, so everything to the left of the green line is excluded. Oh, great, thanks. Oh, perfect. Yeah, so everything to the left of these green lines is excluded, and somewhere in this green band, yeah, you would actually solve what was known as the missing satellite problem. You know, the claimed discrepancy that you see is too small number of small subhalos compared to what you would expect in the simulations. At the same time, thanks a lot, you can compute the self-interactions, yeah, as a function of the, well, this is the self-interaction strength. It's velocity dependent, so you have to do the average, the proper average over this complicated process, which is also why you see these resonances appearing. And then for sure everything to the left of the blue band is excluded because this corresponds to very large self-interaction cross-sections. Yeah, but somewhere in the ballpark of 1 centimeter squared per gram, that was typically used to explain the small-scale problems. Yeah, in particular the cusp versus core problem and what is known as too big to fail problem. Yeah, and then in this kind of model, you can say that, okay, if we actually believe this kind of reasoning, then there's an intersection of these two bands. Yeah, so there's an area, a region in parameter space where you can solve all small-scale problems. Yeah, and the nice thing is that it's a complete dark sector model, so there are no couplings to the visible sector, but you can use cosmology to actually constrain and potentially even measure the particle physics parameters. Okay, so another example, cosmic ray accelerated dark matter. What's the idea? Well, typically you have direct detection, elastic scattering between nuclei and dark matter particles, but if that is present, yeah, then also the, I mean, this is the galactic disk, this is the halo of dark matter particles, but around that there's a magnetic halo where cosmic rays propagate. Yeah, so these high energy cosmic rays would occasionally hit dark matter particles. It's the same physical process, the same cross section, and accelerate them. Yeah, so we actually expect that dark matter in the, at Earth is not only non-relativistic, that's the dominant halo component, but that there's a small subdominant contribution that is highly relativistic. Yeah, and that means that you can actually measure even light dark matter particles, which typically would not have sufficient kinetic energy to trigger any signals in the detectors. Yeah, this can get rather complicated. So this is basically an indication of this. So this is the standard halo model, the velocity dispersion of dark matter particles as a function of the velocity. And then you have these small additional contributions at very high velocities. You can compute all that with DarkSUSY, and also including, like now in the newest version, like arbitrary matrix elements, not just contact interactions like in the first example here, inelastic scattering events and so on. Indirect detection yields, that's very often used, of course, for indirect searches of dark matter. Very many different spectra are tabulated, both from Pythia and alternative tabulations. You can very easily switch between the different yields. And the way this is implemented is that you really only have in your main program, you just call sort of a setting routine, which kind of yields you want to use. And that is propagated then automatically to whatever indirect detection rates you use, yeah, for gamma rays, neutrinos, antiprotons, whatever. For model-specific cases, yeah, all these spectra are always what is known as model independent, yeah, meaning that you only take into account radiative corrections from final states. But in specific models, you can get very strong contributions that are model dependent, like these kind of features here, that you don't find in Pythia or PPPC spectra, for example. These are model dependent. So in general, these are just some examples, and on the web page you can find further examples. So the way this is organized is always that you have like one example here, a plot that was produced with DarkSUSY, or the data were produced using DarkSUSY. Then there's a link to the code example in the example directory and a short description and where it appears. So you can just browse there and get inspired and take that as a starting point of programs that you want to further explore. Okay, so this was just the teaser. I don't know, any questions at this point? Then we can start the actual tutorial. Okay, so I assume that everyone has downloaded and installed the code. So who has managed to produce something like that? Okay, who tried but did not manage? Okay, that's expected. Very good. Yeah, so I mean, afterwards I will have some exercises, and then I will go around, so just make sure to raise your hand and catch me, and then I can take a look. Okay, so just like the simplest thing to check is, I mean, what most often goes wrong if you don't manage is that some of the contributed codes don't compile because you're missing some packages. So just to check out that this is not the culprit, you could try to build the light version. Then, for example, the MSSM module will not build because it relies strongly on contributed code, so then you will just see a cross here, but the other modules can still be tested. Yeah?
I have managed to configure, but then when I tried to make, I also specify the version of the compiler, and it has this problem, pops up with heal mix or something, and it says, and then I open the log, it says something about the make directory, read file.
Okay, I can take a look afterwards. Yeah, so they are typically very system specific things that can happen. So I can take a look. Just let me know. Okay, so for those of you who have managed to at least do the configure step, yeah. So I should stress that for the configure step, so do read the fine print here. Yeah. So if you have gFortran, GCC, then this is always the better option than just running a configure. Yeah, so this should always be your first attempt, because that basically just calls configure with suitable compiler options automatically. Yeah, of course, if you're already an expert user, have installed like hundreds of packages, then you know how to use configure, and then you probably have better options even. But per default, this is the best thing to do, unless you have iFort or whatever. Okay, so what you will see is something like that. Yeah, so there's like an installation directory. And the way this is organized is that all the code is in two main directories, source and source models. So everything that is here is completely particle physics independent. Yeah? So it's organized in subdirectories according to what kind of routine this is. So DD for direct detection, RD for relic density, and so on. Yeah? And the way it is organized further is also that all the files here, so we've tried to have a separate file for each subroutine or function, such that you can that it's easier to find your way through the code. And the file names are also always such that they start in this way. Yeah, so they always start with DS for DarkSUSY, followed by these shorthands then, DD for direct detection, RD for relic density, and so on. So you immediately know what kind of routine this is. All of this is then, after compilation, compiled into this library, which we call the core library of DarkSUSY. Yeah, then in source models, there are different subdirectories corresponding to the code relevant for the different particle physics modules. Each of these subdirectories makes it into a separate particle physics library. Okay, and then, like most importantly, there's in the directory with examples. Yeah, I already talked about some of the examples. documentation. In particular, there's a full manual. And then things that are like more technical. So lib stores the actual libraries. Data contains tons of data tables needed for the calculations. Scripts, I mean, don't touch unless you really know what you're doing. And contrib is basically contributed code, external code. You typically don't need that. Manual, you just create it with a make system as well. It's an extensive manual that comes in two versions. So one with all the function headers and one without. In general, the function headers contain quite a bit of information as well. So for a specific function, you will find more information by looking at the file. That also contains the author, which you can ask then for more details or if something doesn't seem to work. Okay, so then what should you do? I said already that it's Fortran. So DarkSUSY is essentially a library of routines that you can use. So what you need to do, and what DarkSUSY doesn't do for you, is to provide a main program. So we provide examples in the examples folder, and that is typically your starting point. But in general, you write a very short Fortran program linking to the library and using all the functions and subroutines that the library provides. So that means that, well, you need to know some level of Fortran. And Fortran is very, very simple. So a basic Fortran program looks like that. So you always have like a declaration of the program, and then you start with declarations of variables, and then there's the actual program. More concretely, so this include statement, this can, it's basically just a text file. It literally includes what's inside the text file. Typically, it's used to include even more function declarations, in particular global variables, which in Fortran are called common blocks. But it's just a global variable. Then here you have subroutine calls, so functions that don't return anything with call, and functions that return a value look like that, so they are directly assigned to a variable. That's in a nutshell how Fortran works. So not very complicated. One annoying thing about Fortran, at least in the 77 version, is that it has a line restriction. So you can't continue, you can continue to write beyond character number 72, but it's just ignored by the compiler. If you want to have longer lines, you continue in the next line and you start in place number 6, and also the 6 first characters you need to leave empty. This sounds terribly annoying, but you get just used to it. And of course, it's because Fortran is actually quite old, so it goes back to the times of punch cards, and that's the reason why there's this sort of empty space at the beginning. Okay, but that's just a technicality. Okay, so essentially, this like 15-line codes that you've just seen, that's what you need to know about Fortran. You actually don't need more Fortran knowledge in order to use DarkSUSY. Okay, so this complicated program, ds main wimp, essentially does the same thing. And probably you have already tried to run it. So when you do that, you will be asked to test, to add some model that you want to test, and add parameters. So who has already tried to play around a little bit with this? Okay, not very many, so I suggest that we take a 5 minutes or so break where you actually try to do this. You look at the output and at least sort of very roughly try to identify where in the code that output is produced, just in order to get an idea that, you get tons of output with explanations. Okay, this is an indirect detection rate in gamma rays, in positrons, antiprotons, direct detection rate, and so on. So it looks like a complicated calculation, but then in the code you will realize that the call to the corresponding functions from the main program is very simple. That's basically how to, the idea of this program, to very quickly let you identify what kind of calculations you do and what kind of function calls you need for that. And while you're trying, I will move around and try to help those of you who had problems in installation. Okay, 5 minutes. There was a question, or did you have to?
Yeah, so it's just very basic because I'm not sure if I need to download Fortran or what exactly I need to do.
Oh, you need to. On for everyone who has come to this point. So just to explain what is going on. So why does it work this way? Yeah, so the way DarkSUSY is set up, yeah, as I said before, you need to supply a main program. And this main program always links to the DarkSUSY core library, which is particle physics independent, and it links to one of the chosen particle modules. Yeah, and this recompilation that you do, I mean, this linking happens at the compilation stage. Yeah, so when you invoke make. So that is why you can relink using a make command. Yeah, so concretely, I mean, if you would do this at the command line level, you would really write something like that. Yeah, you have like gfortran to compile, -o in order to produce an executable, and then you have linker statements to core and then to either of the two particle physics modules. Yeah, so the whole make system is set up such as to avoid you having to repeat all these inputs and to make these inputs machine independent, at least for most machines apparently. Yeah, so this is, I mean, so who is familiar with make files? Yeah, okay, good. Great. but this is very often the bottleneck, so that's why I included a bit of explanation here about make files. Yeah, so the main take home will be don't be afraid of them, don't be scared, but it's a bit of a threshold to come over. I mean, there's a huge gain once you understand like what you can do with this. Yeah, so the actual make file in this directory looks something like that, so it's terribly complicated. But you can actually recognize what is happening here. Yeah, so this gfortran command, this is just a makefile variable. So during the configure step, this variable is filled in a machine-specific way. So that is why I can use the same makefile, even though you have very, very different computers, and even though on your different computers and system installations, this command would look very differently. Yeah, that's in a nutshell the idea behind makefiles. Yeah, then you can recognize this part here, that's exactly what we have there. And, well, this part here is included in complicated statements like that. So, basically, in the main file, we have then blocks like that, pre-compiler statements, that check which model we have implemented. Yeah, so this is how it works sort of behind the scenes. But this is still a relatively, I mean, from the coding point of view, you don't need to know these kind of things. So much easier, it is the way we've organized these like simpler example programs in the aux directory. Yeah, because there we have example programs that are tailored to a specific particle physics module, so we don't have to specify or provide a system that automatically can switch between different modules. So this is more just a demonstration that you can do this. But in practice, when you get started, just look at these things. Yeah, so if we compare the two makefiles, yeah, for the DS main WIMP, that's what I've just flashed before, and the much simpler corresponding block for a simple program that you were supposed to look at as one of the starting things. Yeah, just calculating the relic density for a generic WIMP. It's a much, much shorter block here. And in particular, this module, generic WIMP here, is just set by hand. And here we have a complicated statement that basically adds additional libraries that you need depending on which module you want to use. But here you can just add them by hand. Yeah, so why I'm flashing this? Well, because of this bottom line. Yeah, so the way you should think about this, of course, it's great to know about makefiles, and it's something you want to learn at some point, but you don't have to like first read up a tutorial on makefiles. The way it works is that you simply take a given makefile, and that doesn't only go for DarkSUSY, it goes for any like more complicated code that you want to install, and then like every of these so-called targets, so when you invoke the make command, you write make something. Yeah? If you don't write anything afterwards, you basically write make all. Yeah? You just can leave it out, the or. And every target, for example, for this file here, OH2 generic WIMP, radical density generic WIMP, yeah, you would write make OH2 generic WIMP, and then these are assignments that are carried out once you invoke the main command. So if you want to use it in your own codes, yeah, you want to write your own little example file like the one that I flashed before, you just copy the example file, you copy such a block from an existing make file, even without understanding what's going on in detail. And the only thing that you have to change is then maybe the module name if you want to apply it to another module, or add additional files that you know that your code will depend on. And the benefit from that is that you have, like, you can compile your own code with the very system-specific compiler settings that are configured during the configure stage. Yeah. So how do we write a known program? It always takes the same form. Yeah? In DarkSUSY, you always have to initialize the code. That's always the first statement. Yeah? Then you do some general settings. You can determine your model parameters either by hand or you read them in from some file or from screen, whatever. Afterwards, you always call a routine that starts like ds_gif model. So what this does is to essentially convert input parameters to relevant like couplings, masses, and so on. Yeah, so for example, Lagrangian parameters to running masses, couplings at the scale that you're interested in, and so on. And then afterwards you call ds model setup, which transfers all the relevant quantities to global variables that the code needs. Yeah, so it's always the same structure. So what you want to do in general, if you want to write your own code, make your own main program, very importantly, you don't modify the downloaded and installed code. Yeah, you just go somewhere else. You create a new directory that is a pristine, empty directory, and that's where you put just a single Fortran file. Yeah, don't interfere with the existing installation, because then you will create like changes that are impossible to track. Yeah, and just in order to be able to compile that, you need to be able to use the make files from the installation. So just copy one of them. You don't have to understand them. Just copy them and remove all the blocks that you don't need, all the targets, and modify the one target that you want to use. Typically, you just need to change the name. You change the name of the program. And then you just type make in your new directory, and everything should work out of the box. Yeah? So, of course, you can do it another way, but this is really the strongly recommended way to do it. Okay, just try this. This is the next task. Yeah? Literally, use this OH2 generic WIMP, copy it somewhere else in a directory which is completely unrelated to your DarkSUSY installation, rename it, and compile it using make. 5 minutes. Okay, and then I can continue to move around for people who struggled with the previous stages. Did you try to? Oh, I don't know. Something.
I have like the 14, I don't know how to uninstall it and reinstall it. I think with the 13 is going to work. But even if I do like, I did uninstall.
Yeah.
But now...
What version do you have?
I still have the 14.
Okay, I have version 15, it works.
Oh,
if you just install with brew or something like that.
I see, 15 works as well. So I've noticed that some of the new GCC versions, they are, either buggy or in the code there's something that doesn't exactly follow the conventions, which works for some versions and not others. Yeah.
Because like if I do like brew install GCC,
Yes.
You can continue to try. So one thing that can be an issue when you copy and paste things, that's the one annoying thing about make files, that Makefiles strongly distinguish between tabs and spaces. So depending on your text editor, if you just copy a block, you think that you do exactly the same thing, but it doesn't work. And the most common error that happens is because of exactly that. You have a tab in the original file, you copy it, and it is converted to spaces, and that gives a syntax error. Yeah? So watch out for that. Okay. So now we do a real problem. I mean, this was just copying and seeing that we can compile a given program in a different place. Yeah, now we want to have actually a simple main program and run it from a different directory. So the task is to write a super simple model, like max 15 lines of Fortran, to just compute, to set up the scalar singlet model and to calculate the relic density. Now, of course, you may remember that I had an example program. Yeah, that's exactly what this program does. Yeah, so we set up DarkSUSY, we call the model with some parameters, followed by this model setup as always, and then we simply calculate the relic density. Yeah, so you don't have to copy that. It's actually on the school homepage, so you can just download this text file and try to compile it with the same setup that we used when we copied the file. So this is very close to the previous exercise. Just now you actually need to compute a new piece of code. Yeah, but you can realize that the block in the Makefile, you don't need to understand in detail what's going on, but you just need to copy it and just change the module name, because now we are doing something that doesn't work for the generic WIMP, but for the scalar singlet model, which is called severe Z model. Yeah, you just have to identify any of the blocks in the original Makefile, copy it, and change the name. And then it should work. So maybe I just show this in practice, such that also those of you who haven't sort of been able to run it so far, that it's actually simple. So let's see. So this should be empty. Yeah. So this is the empty directory, which is sort of unrelated to the DarkSUSY installation. Yeah, so I simply copy there the code. This is the scalar singlet example. This is these 15 lines of code that I've shown you before. This didn't work because I didn't specify the target like this. Okay. Yeah, so this is this code that I had on the screen, and now we want to compile it. Yeah, so our directory so far only contains this code, so we need a Makefile. Yeah, so we basically want to copy the Makefile that is closest to what we want to do, and we know that the simplest Makefiles are in the example awk folder. So we copy it from there, and then we have to know where we have our DarkSUSY installation. So on my machine, it's here, DarkSUSY, and then I want to use the same release as you're using. So 640, examples, AUX, and then we have the Makefile. Yeah, by the way, you can easily see that you haven't compiled yet and installed your code if there's only a Makefile.in. Yeah, this is sort of the basic Makefile before the configure script has been run. Yeah, so you really need the Makefile, not the Makefile.in. So the Makefile contains all your system-specific information. So we copy this here, and then we can open it with any text editor. So I start my code, Makefile. Yeah, and then, okay, so this is actually documented in some sense, but just treat it as a black box, really. So what I said before is that what we want to do, we have a code that is supposed to run a simple program for the scalar singlet case. Yeah, so you identify just in this list of targets something that sounds like scalar singlet for example, this one here, OH2 scalar singlet. Yeah, and then you literally replace all the occurrences of that with your module name or your file name. So I don't remember how was it called. It was called scalar singlet example. Replace OH2 scalar singlet with scalar singlet example. Replace, and replace. Yeah, so then we've done this for an entire block. Yeah, and then in principle we could delete all the other blocks because we're not interested in all the other programs. They don't exist anyway in our directory. Yeah, also you don't have to do that, but it makes your make file smaller and tidier. And there are more. Yeah, each of these blocks corresponds to the makefile instructions for one specific simple example program. And then in this all target, we only want to have this example left. Yeah, because the others actually don't exist now anymore. So if we would just type make, that would cause an error because we don't have the code. So that's the only thing that we should need to do. Let's test. So we just type make, and it actually compiles. Yeah, and the nice thing is that with this simple copy and paste prescription, we have automatically access to the entire installation, including all the highly system-specific compiler specifications and settings here, for example. Yeah, so you don't have to understand any of this, but you can still use the full functionality of the system. So let's see, it compiled without problem. Let's see that it also runs scalar singlet example. Yeah, it initializes and it plots the relic density. Yeah, and I mean, I appreciate that it's a threshold to get used to like using the console and installing things in the first place. But what I want to demonstrate is that once you have this at place, this working, yeah, which is not DarkSUSY related, but more like getting into using consoles, it's super simple. Yeah, I started from a completely empty directory. Yeah, and within 10-20 seconds, I can like actually compile using a make system, can compute the relic density in this case. Yeah, so that's the general idea. And I did it in a way, I mean, now of course I can start to modify the code here. Yeah, so if I look at this code, yeah, then of course I can directly edit it, I can change parameters, I can do other stuff, and afterwards I just have to type make and run again. And whatever I change here will not touch at all my installed DarkSUSY version. Yeah, so you never run into the risk of modifying something which you have to undo, and maybe you at some point can't reproduce an error, you have to reinstall everything and so on. It's a very clean way to do things. Okay, questions so far, other than my G4 doesn't run? Yeah.
Question about like a practical question. The version of DarkSUSY that you use depends, like is specified in the make.
Yes, very good. So another advantage with these makefiles is, yeah, so this is sort of like next level of user expertise. You can try to understand what is going on, and then you see that there's this line here defining a prefix. Yeah, it tells you, actually, it's a link to the directory where I have installed DarkSUSY. Yeah, and now I know that if I have installed a different version of DarkSUSY in a different directory, all I have to do, in fact, is to just change this here, which is a great way for development. Yeah, you can actually have a DarkSUSY version which you keep modifying, which is your actual private one, but which you don't modify while you're testing main programs. Yeah, the only thing that you need to do is to change this one line in the main file. Yeah. Okay, other questions? Okay, so then let me very briefly come to the next point, and then I guess we have to call it a day almost. Okay, so this is basically the solution that I just demonstrated. Yeah, we create this Fortran file, we copy it from somewhere, we add just this block, and then, well, in order to work, you must make sure that you don't delete this file because it's a variable declaration. Just a technical. Okay, and I encourage you, I mean, I will put this online. If you want to try it yourself, you can try to do the same thing for example, the generic wind model. Yeah? There are minimal changes that you need to do, and then you can calculate in a one-line fashion the relic density for any input parameters. Okay, so now let's get to the modularity that I was stressing. So I already emphasized that you have a main program that links always to two things, always to the core library and one of the particle physics libraries. And you cannot link to two particle physics libraries for consistency. Now, how does this work in practice? Well, of course, the core library needs to get some information from the particle physics libraries. Yeah, and this is implemented in such a way that the amount of information that is passed is absolutely minimal and only works through what we call interface functions. Yeah, so this invariant rate for the tabulation of the thermally average annihilation cross-section, for example, is an example of such an interface function. Yeah, so meaning that the main library doesn't have to know anything about the particle physics. It just tells the particle physics module, please give me a function with a certain signature. Yeah? It's a function that in this case only depends on one variable, namely the center of mass momentum, yeah, and returns a rate. How that rate is calculated, this entire set of functions here, thermal averages, solvers of the Boltzmann equation, very complicated stuff, doesn't need to know about this. Yeah? And in a sense, from the point of view of the code architecture, the set of interface functions actually defines the particle module. Yeah, of course, you as a user think of a particle module as, well, a set of Lagrangian parameters, interactions, and so on. But for the code, it's just a finite and very small number of functions. And try to think along this way, because that allows you to understand how modular the code is. And actually, you can even define particle modules that are incomplete, in the sense that the particle module can, for example, only provide the invariant rate. Yeah, in which case you could, for example, run the simple program that I showed you before. You can calculate the relic density. But if you write a corresponding simple program to calculate a direct detection rate, it will fail already at main stage, at compilation stage. Because it tries to compile a rate calculation function, direct detection coupling, which it needs to calculate the rates. It doesn't find that because the module doesn't provide it, and then it cannot compile. But it will tell you at compilation and make stage which function is missing. Yeah. And the core library doesn't care about how you provide these things. Yeah, so these can be very complicated ways of calculating, for example, the invariant rate in the MSSM. It's super complicated because you have all these co-annihilations. It actually takes a significant amount of time to even compute the invariant rate. Yeah, but you can also bypass it. You can use another program, some, I don't know, 5-loop calculation tool that just tabulates this. Yeah, maybe you've run this on a cluster for a week, just tabulated it, and provided here the same function with the same signature, and then the thermal average averages, the tabulation, the solution of the Boltzmann equation, and so on will work in the same way. So that's how the modularity is implemented. Related to that, there's one important concept, and that is the concept of replaceable functions. So almost all functions you can replace at linking stage. And that's a concept that is similar to what I tried to stress for the main program, which you should keep always separate from the code. Yeah, so you can, for example, I mean, this is a concept that is particularly useful for interface functions. Yeah, so say that you have a particle module like the ZRZ. Yeah, you calculate the relic density, and then you want to change something. You want to say that, oh, but actually the Bright-Wigner propagator I don't like. I have recently read a paper where the Bright-Wigner propagator is parameterized somewhat differently. I want to provide a different invariant rate. Yeah, don't go into the code and change it, but write your own invariant rate function, which of course in practice you would do by first copying the existing function to your private directory and then modifying that. And then tell the make command at linking stage to override in the executable with your new version. Yeah, so this is the idea of a replaceable function. And that is set up in such a way that if you, for example, do this, now I always use this example for the invariant rate, it will automatically propagate everywhere in the code. Yeah, so the same invariant rate is, for example, used not only in the relic density calculations, but also in the indirect detection routines. Yeah, so if you want to calculate like antiproton yields, neutrino yields, whatever, you will automatically use the same replace function. While if you were to change it directly in the code, there's always the risk that you miss some dependencies. So just to spell out this example more explicitly, if you want to change something, invariant rate, then, for example, a simple example here. You just want to add another factor. Don't directly change anything in the installed in the installation directory, but instead replace it. Concretely, copy the relevant function, this dsn unwx, that's the invariant rate, copy it to your private directory, change it there, add such a factor, and then make sure that at linking stage this is replaced, meaning that at linking stage all the executables that are built use your version of dsn_wx and not the one that is provided by the downloaded version of the code. So I guess we don't really get there, but I mean, this is the next thing that you could try. It's really easy once you've done it once. And there's an example in the examples folder. So there's a code that is called generic WIMP omega h squared, which we've already used. But there's another target which is called generic WIMP omega h squared _ threshold. And that's exactly doing this. It uses the same code, the same main program, but replaces the invariant rate. So just copy that block from the make file rather than the original one, change names, and it should work in the same way. So that's the next task for those who are still learning. But I can also go around and answer other questions, also like those that you maybe have for the other problems. So we still have 15 minutes, I think. Oh no, we are already over time. Okay, so then this is a homework problem if you want to do this. And let me know if you actually want to solve it, but don't manage and you want more help with this. So thanks for contributing.